All right, so we begin today looking at chapter 16. Chapter 16 is our last equilibrium chapter in the text. And so if we look at it from this point, up until this point, basically all we've talked about is chemical reactions. We've talked about how fast they go, and we've also talked through equilibrium about how do we determine how a reaction is favored in terms of, does it favor the products, does it favor the reactants, does it go somewhere in between? And a lot of our study in the last chapter was all about acids and bases and how substances interact with water to create hydrogens, hydroxides, acid and base qualities that we could measure with pH. We're going to continue our look, and we will spend exactly 1 week. So today is Wednesday. We will stay in this topic until Tuesday next week. So from that perspective, we are going to get a little bit of breathing room in terms of after the chapter 15 quiz, we're not going to see another quiz until late next week over this topic. But what we will see in this is just another extension of equilibrium to water-based solution systems. And we're just going to be extending the challenge a little bit. So thus far, everything's been somewhat straightforward. And it hasn't felt necessarily that way because we've been sprinting through chemistry here instead of kind of taking things one step at a time. We're learning multiple concepts at the same time. But what we'll find in this chapter is that there isn't a whole lot of stuff that is truly new. There is going to be some stuff that is new in the sense that we haven't considered this particular angle before. And there will be some equations that we use to help us try to deal with those new perspectives. But a lot of the stuff that we're talking about is essentially the same. It's just a different application. So when we start to look at what this chapter has, we can see that this chapter basically breaks down into 4 concepts. And we will be covering each of these concepts in turn over the next 4 days, and then kind of cleaning things up and reviewing these things on that 5th day. The first thing that we're going to look at is something called the common ion effect. The common ion effect is us taking Le Chatelier's principle and using Le Chatelier's principle to tie it to something more quantitative. So let's say that we have an equilibrium system and we add some aqueous product to it. We know, based on Le Chatelier's principle, that that aqueous product is going to shift everything toward the reactant side of the equilibrium. That's as far as we took Le Chatelier's principle. Now we're going to look at it and say, okay, what does that actually mean? If I have an acid-base system and I shift the equilibrium toward the left, what does that mean for the pH of that system? We'll take a look at buffers. Buffers are chemical solutions that are naturally pH change resistant. And we'll get into why they are pH change resistant. And it largely has to do with, again, kind of coming back to this idea of the common ion effect. We'll look at acid-base titrations. Now, we already know quantitatively how to do a titration calculation. That's not actually what we're after here. what we're going to explore is how can we use a titration to actually solve problems about the acid itself. If I give you an unknown acid, you can do a titration and tell me what its concentration is. Could you tell me what it is? Not just by doing a titration. We'd have to look at it in another direction. So what a titration curve will do is we'll be able to actually graph the titration as it is happening. And we can use the information from that graph to identify key factors about the acid itself, like its Ka value, which we could then use to figure out, okay, here's the Ka value. There are a list of acids about this long that it could possibly be. So we've narrowed our focus. It was every acid is possible. Now we know it's these acids are possible. We'll take a deeper look at solubility equilibria and try to put some better clarity on the concept of solubility. You know, we have solubility rules that we generally use. Chlorides are soluble except for when with silver, lead, and mercury 1. Sulfates are generally soluble except for with barium and calcium and lead and mercury and We've used those as general guidelines to help us predict kind of the most common exceptions to solubility. But we said it at the time, and we're going to reinforce it here. Solubility is a continuum. There isn't a line that says, okay, this is soluble and 100% of the ions are going to dissolve, and this is insoluble and none of them are going to dissolve. The reality is solubility is an equilibrium expression. And whether we view something as soluble or insoluble depends upon the value of that equilibrium constant. The larger that equilibrium constant is, the more soluble we consider it. The lower it is, the less soluble we consider it. And then taking that last idea of solubility and just applying it to some things. We're in the midst right now of some qualitative analysis experiments. We already did one. We're in the middle of a second. We start a third one tomorrow. Why do those procedures work? Well, it comes back to this idea of solubility and using something called selective precipitation. Because this substance is way more soluble in chloride than this substance is, we're going to use chlorides to separate them from each other. Then we'll use this property to separate these ones from each other still. And we can just go down the line to do that. We'll also take a look at some individual factors that can affect solubility. And the good news in that is we've already explored some of that in lab, at least from a qualitative standpoint. We've talked about the formation of complexes. We've talked about acid-base reactions for certain kinds of hydroxide compounds. We've done some of that already. We're just going to reinforce it here. But for today we are going to focus mainly on the common ion effect. And we're going to take our knowledge of the common ion effect and start to introduce the concept of buffers, because buffers are a direct application of this effect. And that'll lead us well into tomorrow, where we actually get into some of the calculations and the nitty-gritties around buffers themselves. So what do we know about the common ion effect? Well, we know that it's a shift in equilibrium caused by the addition of another ion into the system. So let's take this reaction system here at the bottom, for example. according to Le Chatelier's principle, if I had this carbonic acid and water system making the bicarbonate ion and the hydronium ion, the addition of any of these conjugates to the system would cause a shift in the system to relieve that stress. So if I have this carbonate system and I add some baking soda to it, sodium bicarbonate, the bicarbonate ions in that system are going to raise the concentration of the bicarbonate, and that's going to shift the whole equilibrium to the left. If I shift the whole equilibrium to the left, I'll notice an increase in the concentration of the carbonic acid, which will probably come off in the form of carbon dioxide in that case. And I'll see a decrease in the concentration of that hydronium ion. A decrease in the concentration of that hydronium ion should indicate a pH that is going upward, more positive, because there's fewer ions of hydronium present. So that's the qualitative side of this. And this is something that we've explored already. We explored it in chapter 14 when we looked at Le Chatelier's principle for the very first time. Now we're starting to see it applied into other systems, into acid-base systems. And we can tie it into some of those concepts that we associate with acid-base systems as a result. Things like pH. So, like we said, as we would expect, if we increase that concentration of the bicarbonate ion, it's going to shift everything left. And so the hydronium concentration will decrease. Which would mean that the pH should increase or become more basic. So let's take a look at an example of just this kind of manipulation. What is the pH of a solution made by adding 0.2 moles of acetic acid to 0.1 moles of sodium acetate in enough water to make 1 liter of solution? So the equilibrium expression here, we've got the acetic acid equilibrium. Reacting with water. To make hydronium ion and acetate ion. Our initial Ka for acetic acid is 1.76 times 10 to the negative fifth. The only reason I know that one off the top of my head is because we use it so much. Acetic acid is kind of like the prototypical weak acid. It's in every problem. Now, here's where these problems can get tricky, because if we're building out our ice table here, we're starting with, it's a liter of solution, so all the moles can get turned into molarity immediately. We're starting with 0.2 molar acetic acid. We don't have any hydronium initially, but we do have 0.1 molar acetate. Now, since we have no hydronium, we know that the whole equilibrium is going to move toward the products, because you have to have something of everything to have equilibrium. So at equilibrium, this is what we have. 0.2 minus X for the acetic acid, X for the hydronium, 0.1 plus X for the acetate. Our Ka value, 1.76 times 10 to the negative fifth, would be equal to X times 0.10 plus X over 0.20 minus X. And so what we have here is the makings of a pretty messy quadratic. 1.76 times 10 to the negative fifth times 0.2 is 3.52 times 10 to the minus sixth. So if we combine terms, get everything onto one side, 0 is equal to X squared plus 0.1 plus 1.76 times 10 to the negative fifth. So 0.1000176X minus 3.52 times 10 to the negative sixth. So we're gonna have to pull out one of our favorite equation solving tools here. So A is equal to 1. B is equal to 0.1000176. C is equal to negative 3.52 times 10 to the negative sixth. There we go. So again, two answers come up. One is going to be nonsense. Obviously, we can't have a negative concentration. 3.52 times 10 negative fifth is our value of X, which is also our value of hydronium. And so the pH would be equal to the negative log of 3.52 times 10 to the negative fifth, which would be 4.45. So when we have these common ion effect problems, they can often present for us difficulties in terms of just how to approach them. Now, luckily for us, this would have been a situation we could have used the 5% approximation here. And when you use 5% approximation in common ion effect kinds of problems, it doesn't just affect the minus x. It would also affect the plus x if that term is large enough as well. So 0.0 or 0.2 times 5% is 0.01. So 1 times 10 to the negative second. So we're talking about 3 orders of magnitude difference. That's more than enough. 0.1 times 0.05 is 5 times 10 to the negative third. 2 orders of magnitude. That's far enough. We could have, with the 5% approximation, ignored both the plus x and the minus x term. If we had done that, we would have had Ka is equal to x over 2. 0.1 divided by 0.2 is 1/2. So multiply by each side by 2, you would have got 3.52 times 10 to the negative 50. We're going to have the exact same place. So, like I said, you can apply the 5% rule to these kinds of problems as well, if the Ka value is small enough and your concentrations are large enough. Now, if we don't have that, then it's going to be really hard to apply that approximation. You would have to solve using this similar ice table quadratic approach. But we can actually even do one better than that. What if we didn't have to do an ice table at all? Getting some thumbs up, getting some happy smiles. In a situation where we are seeing the common ion effect applied to an acid-base system, what we can apply is something called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation will generate for us a pH of a solution, provided that we have concentration values of the conjugate base and the conjugate acid. If we don't have both, we can't use this equation. We have to revert to normal ice table. But if we do have both, boy, does this equation make things a lot easier. And it makes things easier in another sense as well. And I love this application of the Henderson-Hasselbalch equation. Since we are talking about the same solution in this case, we don't even need molarities. And the reason we don't need molarities is because if I have moles over liters in the numerator and moles over liters in the denominator, and I know that these 2 liters are equal, then that also means that I can cancel them out. If the denominator of both fractions is the same number, I can take it out of the equation. And why that's important is because a lot of times we make solutions like these where we're combining one solution with another. And so the 2 solutions dilute each other in the process of combination. So if I have to use calculations of concentration, I have to first apply the dilution equation to each equation, then use the Henderson-Hasselbalch equation. Well, we can actually simplify it a little bit. If the liters are equal to each other, I just need to know the number of moles of each. I can just put the mole values in there because it is the same solution. So it is going to be equal in volume when they are combined. So what does the Henderson-Hasselbalch equation actually give us? Well, when those 2 concentrations are the same, when the concentration of the base and the conjugate acid are equal to each other, that fraction becomes 1. And the logarithm of 1 is equal to 0. And so if that happens, then all that's left in the Henderson-Hasselbalch equation is pH is equal to pKa. And remember, pKa, we talked about this yesterday, pKa is equal to the negative log of the Ka value for the conjugate acid in this case. When our concentration of base is greater than that of acid, what we'll see is that the logarithm will trend upwards above 1. Logarithms greater than 1 are going to be positive numbers. So we will see that the pH of the solution will tick positive toward the more basic side, which should make sense. The base is more dominant, so the resulting solution is going to be more basic than normal. And if the acid is bigger, the fraction is going to go below 1. Logarithms of fractional numbers are negative. And so the pH will dip onto the acidic side of the ledger, which again should make sense. We have a higher concentration of acid present. It should be more acidic than expected. So when we have this kind of solution, where we have an acid and its conjugate present at the same time. By the way, this is what a buffer is. That is the definition of a buffer, is a weak acid and its conjugate base present in the same solution at the same time. But when we have this, what we can consider is normal would be the pKa of the acid. That's where we've got an even balance of the 2 conjugates. And if we have an uneven balance of the 2 conjugates, we'll see that the pH leans off of normal toward whichever side has the greater amount. So if the pKa is 4, but the ratio of base and acid is slightly basic, we'll see that that pH will trend up above 4 just a little bit toward the basic side. And if the ratio is a little bit heavier in acid, we'll see that it'll trend just a little bit more downward toward the acidic side of the scale. Now, if we are looking at basic solutions, so let's say that we're looking at, instead of acetic acid and acetate, we're looking at ammonia and ammonium ion. Well, we could use the Henderson-Hasselbalch equation, but we would have to turn that Ka that Kb for ammonia into a Ka for ammonium to do it. Now we could do that. If we're told that the pKb of ammonia is 4.74, we can turn that into a Ka by subtracting 4.74 from 14. We're back in business. The other way we can do it is we can modify the Henderson-Hasselbalch equation to allow us to use the pKb in the first place. And so this isn't in your equation sheet, but it is a useful application if you don't want to do this subtraction to get Ka when Kb is present. If you are dealing with a basic buffer system, ammonia and ammonium ion, quinoline and hydroquinoline, aniline and anilinium ion. Pick your favorite nitrogenous organic and the one that has a hydrogen attached to it also. If you're dealing with those systems, you're going to be given a Kb value. And so, like I said, your options there are either to turn the Kb into a Ka, which we know how to do. Divide that number into 1 times 10 to the negative 14th. 10 to the negative 14th. Or you can use this modified version of the Henderson-Hasselbalch equation. And really, the only difference, I'll write the original below it. The only difference between the equations is the perspective and what that fraction in the logarithm looks like. Calculating pH for acid versus pOH for base. Using Ka because it's an acid versus Kb because it's a base. Those two things kind of make sense. If I'm dealing with a base, I'm going to deal with pOH, I'm going to deal with Kb. Only difference is the flipping of that fraction. So the way that we go about it really doesn't matter. There's lots of ways to solve these kinds of problems. It's the manner in which that we attack the problems that ultimately makes the difference. And making sure that we interpret the results of that appropriately. what is the pH of a sample of river water at 25 Celsius in which the concentration of the bicarbonate ion is 1 times 10 to the negative 4th molar, in which the concentration of the carbonic acid is 1.4 times 10 to the negative 5th molar. So we're missing a value here. The value that we're missing is the Ka for carbonic acid. So we're gonna have to pull that up. All right, so the Ka for carbonic acid is 4.4 times 10 to the negative 7th. So instead of setting up an ice table here like we would have for the previous 2 chapters, we're going to use the Henderson-Hasselbalch equation because the Henderson-Hasselbalch equation is specifically designed for these so that we don't have to make ice tables in the first place. pH is equal to pKa plus the log of the concentration of base over the concentration of the acid. To find the pKa, I need to take the negative log of the Ka value, 4.4 times 10 to the negative 7th. And then the concentration of the base would be the bicarbonate ion, 1 times 10 to the negative 4th molar. And carbonic acid would be 1.4 times 10 to the negative 5th molar. My molars cancel out. Okay, when we do these calculations, we need to remember our Sig Fig rules for logarithms. And remember, it's the number of digits, the number of significant figures that went into the logarithm become the number of decimal places that come out of it. So 4.4 times 10 to the negative 7th, I have 2 significant figures. So I'm going to need to carry 2 decimal places. The opposite of that logarithm would be 6.36. One times 10 to the negative 4th divided by 1.4 times 10 to the negative 5th. Two significant figures go in, 2 decimal places come out, 0.85. Now, in this particular problem, the next point is kind of moot because we have the same number of decimal places in our addition. So we don't need to worry about any kind of rounding characteristics here. But if that were the case, we have to remember our sig figs for adding. It always comes down to the number of decimal places and rounding to the fewest decimal places in that circumstance. Here it didn't matter. In other cases, it might. 6.36 plus 0.85, total 7.21. All right, any questions with this example? All right, I want you to try this one then. We've got a hydrofluoric acid fluoride equilibrium system. Concentration of hydrofluoric acid is 0.1 molar. We are also told that there is 0.2 molar HCl present. Ka for hydrofluoric acid is 6.3 times 10 to the negative fourth. Now, you're not going to be able to use the Henderson-Hasselbalch equation here. And the reason you're not going to be able to is because we don't have a buffer system here. If we draw out our equilibrium system, notice we haven't been told anything about fluoride. If we had been told something about fluoride, yes, Henderson-Hasselbalch equation would apply here. But this 0.2 molar in hydrochloric acid means that we have a 0.20 molar solution of H plus and 0.20 molar solution of Cl minus. Remember, H plus is the same thing as hydronium. So this hydrochloric acid is creating a common ion effect, but not with the conjugate base. So pick that up and let's see what you can do with it. And we'll talk about it in a couple of minutes. All right, let's see how we're doing. So we've got the initial setup. We've got our ice table set up with the initial line. We know that we're going to gain fluoride and we're going to gain hydronium and we're going to lose hydrogen fluoride. So at equilibrium, we would be 0.1 minus X for hydrogen fluoride, 0.2 plus X for the hydronium and X for the fluoride. Now, this example is a little bit closer than the first one we did, but we could use the 5% approximation here. And it really wouldn't make too big of a difference on our values. So that's what we're going to do. So 6.3 times 10 to the negative fourth is equal to 0.2 plus x multiplied by x over 0.1 minus x. With our 5% approximation, again, we're not more than an order of magnitude off if we do those approximations. So I can get rid of the plus x and the minus x here. That's going to simplify this a good bit. This expression is approximately equal to 2x once I take the 0.2 and divide it by the 0.1, which means that to two significant figures, 3.2 times 10 to the negative fourth molar would be our x value. And that would also be our fluoride concentration. Now, when we add 3.2 times 10 to the negative fourth, 2.20, rounding to two decimal places, we still end up with 0.20. And if we did the same thing here, we'd end up with 0.10 here. The value is just not big enough to make a noticeable roundable difference in those initial concentrations. So the pH would be equal to the negative log of the hydronium concentration, which is 0.20. Which to two decimal places would be 0.70. So you might be thinking to yourself, well, hold on, this is a weak acid. Why is the pH so low? Well, we have to remember that we added a strong acid to it as a demonstration of this common ion effect. So what we're seeing in this pH is the presence of that strong acid, not really the action of the weak acid. So what the strong acid did was it basically held that weak acid, held its equilibrium on the reactant side even more, and made it less likely for that fluoride to pop off. No, because remember, pH is the negative log of the hydronium ion concentration. When we were doing the other calculations for acid and base, we only ever take the logarithm of the hydronium or the hydroxide concentration. Hydronium if it's an acid, hydroxide if it's a base. We didn't take the conjugate's p-value. So if you took the negative log of 3.2 times 10 to the negative fourth, you didn't find pH or POH, you found PF, whatever that is. To do pH or POH, you either need the hydronium concentration for pH or the hydroxide concentration for POH. If that label isn't in your equilibrium, you can't use it. All right, any other questions from this example? So yeah, this one was a little bit on the trickier side just because we were asking you to do something. If you were on autopilot and you took your X value and you immediately took the logarithm of it, that was the incorrect interpretation. You have to understand what your X is actually telling you there. All right, let's go ahead and take a 10-minute break. 9:25, come back and we'll resume.